Hey guys, it's Mr. Ray here with our last lesson of the course. We're going to wrap up linear system unit today. Um, we've looked at two methods of solving linear systems in the previous two lessons. The first method was called substitution, and then we had elimination. Hopefully you've had lots of practice of that. That's very important. So today what we're going to do is finish off the unit and the course with some word problems related to linear systems. Um, we've done a couple of them already in the other lessons, just to kind of warm you up. So basically, linear system word problem would be um, anytime you have two unknowns. Okay, so it's not like solving a linear equation where you just have an x and you solve for x. In this case, you're going to have two variables, could be x and y. Now, when you have two variables, you can't solve for them with just one equation. So you always have to have two equations, and that's what you notice when we have a linear system. It's always two equations, both with two different variables, the same two variables in each one. And then we know how to actually solve for x and y, or a and b, or whatever the variables happen to be. Okay, so these word problems, they're not going to be, they're exactly what it says, word problems, just some sentences with some information. So you actually have to create um, you have to create the linear system by yourself, and in order to do that, you have to define your two variables. Those are going to be let statements. So let x represent, let y represent, then you make your two equations, and then you just go and solve it like you have in the first two lessons, and then you wrap it up with a word answer, okay? So before we do that, I just wanted to show you, you may see something like this on the assignment, okay? And this is actually something we're going to be doing in this lesson as well, so I just want to let you know this is always an option. So I could give you a really scary looking linear system with for example, I could give you a linear system that looks like this. 3/8 x minus 1/2 y equals, I don't know, 3/4. Here's my first equation. And then let's do some decimals in this one. Let's go, I don't know, 1.27x minus 2.3y equals 13. Okay. Now, if I gave you that, I can sense through the screen already a lot of tension. This would be very difficult to solve if you don't know that you can actually manipulate these two equations and create like a brand new linear system, which is the same, represents the same linear system as this, but the equations are different. Okay, so for example, let's start with the second one, the decimals. Decimals are always easier because maybe I want to say I don't like working with decimals. I want everything to be nice integers. So what would I have to multiply all, well, what would I have to multiply all three of these by to get all three the number parts to be integers? Well, that 13 is already okay. The negative 2.3, if I multiply that by 10, it would turn into minus 23, so that'd be okay. But if I multiplied this one by 10, that wouldn't be enough, right? That would turn it into 12.7. So, but if I multiplied by 100, in other words, move the decimal place 2 to the right, that would take care of that. It would also take care of this as well. It doesn't matter if we multiply this by any number, it's still going to be an integer. So what I'm going to do here is multiply everything in equation 2 by 100. I'm going to get 127x minus, now this, remember this isn't going to be minus 23 anymore because I'm multiplying by 100. So I'll move it two places to the left, so that's going to be actually minus 230y. And you still have to do this side, even though this one wasn't a problem before. You have to multiply every term by 100, so that's equal to 1300. So that's my new equation here. And now I don't have to worry about these nasty looking decimals. And I can do the same thing with fractions. I can pick a number that I'm going to multiply all three of these terms by that's going to turn them from fractions into integers, okay? And you can kind of tell I got an 8, a 2, and a 4 on the bottom. So if I multiplied all three of these by 8, it's going to take care of all three of them, okay? Because 8 is a common multiple of 8, 2, and 4. So if I multiply all these by 8, that's going to be 3x. That's going to be 8 over 2, so that would be minus 4y. And this would be 24 over 4, which is 6. And there's my new version of equation 1. So I've got this brand new looking, shiny looking linear system. I'm not going to solve it. I just wanted to show you can turn fractions and decimals into integers. So this would be something we would do. In fact, we will see some word problems where we create a linear system with some decimals. So if you see that on the assignment, you can always change it into a nicer linear system. Okay, it's not going to, by solving this linear system, it will have the exact same solution as this one, but you can see it's a lot nicer looking. I'll use my techniques like before. I don't think I would use substitution here, but I definitely could use elimination. Okay, so that's something that normally we'd take a half lesson on as some extra practice, but we're kind of moving a little faster than normal in this unit. We've skipped a couple of lessons already. Okay, so we're going to do 4 word problems. All 4 of them are different types. There's 2 that are that have a lot of similarities on. So I'm going to actually change the order I do these to go from basically easiest to most difficult. But before we do that, just a summary here. You can solve linear system using any of the 3 methods. Obviously we didn't do graphing, but we did substitution and elimination. So choose the method that works the best, and that's the point here. There might be an advantage to using substitution, or it might be better to use elimination. So I know a lot of students will just do elimination for all of them, and that's fine. But if you see one's set up really nicely to do substitution, go for it. Okay, but don't make it more difficult than it has to be. Don't force it to be a substitution if you're going to end up with all sorts of nasty fractions. Okay, different problems, word problems will have different strategies, and we're going to look at each of those. Typical problems can be grouped into one of these categories: numbers, money, investment, mixture, and distance, speed, current. So that's the 4 categories. We'll do one of each, okay? And you should be prepared for the assignment. I could give you, I don't know, I could give you 3 of the 4 different types. So make sure you understand each of them. Okay, so I'm going to start off with number 1. I think this is always my favorite math question in grade 10 because it's so simple looking. You may not even realize it's uses a linear system to solve it, but let's just read it. On Darwin Farm, there's a total of 50 chickens and 50 chickens and cows. So if you add the chickens and cows together, you'll get 50. If there are 118 legs, like if you added up all the legs of these 50 animals, there would be 118. Kind of a weird way of counting. How many chickens are there? Okay, so if you look at this, there really is 2 unknowns. There's the number, how many chickens are there, and how many cows are there. Okay, so before I even think about creating a linear system, I'm going to define 2 variables that represent those unknowns. So now sometimes I'll use x and y, but I think when you're doing word problems, it's a real advantage if you can use variables that relate to what it represents. X and y can get a little boring, but it doesn't necessarily give you a lot of information. Okay, so I'm going to be a little bit creative here. If you want to stick with x and y all the time, that's fine. You can use any variables you want. So 50 chickens and cows, how many chickens are there? Now, we also don't know how many cows there are, so I'm going to do a variable for each because I'm going to need that. So I'm going to now, here's the problem. I can't use C. Well, if I use C for chickens and C for cows, I can't do that. So I have to pick a different variable. So I'm going to actually use K for chickens and W for cows. Okay, so let K represent. Now, I don't want you to just say, I think I've said this before on other word problems, on previous lessons. Don't just say let K represent cows, because that's not very informative. What is it about the cows? What is K about the cows? Well, it's the number of cows. So you got to say what it represents. Let K represent the number of cows. I know it sounds simple, but it could represent other things too. It could represent, you know, it could represent the weight of the cow or the height of the cow or, the eye color of the cow. Who knows? So this is very exact. You're not guessing at what K is. Represent the number of chickens. Okay, now if you do a good job doing the first one, well, the second one's really similar. So I'm going to, like I said, I'm going to use W for cow. So I'm going to use a double quote every time the word's the same. So let W represent the number of cows. Okay, and now it's very clear. K is the number of chickens, W is the number of cows. Now I go back to the sentences and I read them with a bit more. I'm looking for information I could use to make an equation. So the first thing I see is there's a total of 50 chickens and cows. So total means you're adding up the chickens and cows. So you're basically taking K, adding it to W, and you're going to get 50. So that is your first equation. And in a lot of these word problems, it's a very similar first equation. A lot of times it's just adding up the two unknowns. Okay, not always, but a lot of times it is. Okay, now the other thing is a little more difficult. So don't give up. Just try to think your way through it. So if there are 118 legs, okay, well that means I'm going to get, some of these 118 legs are from the chickens and some are from the cows. So how could I make an equation? Well, for sure I'm going to, it's going to be a total of two things. Okay, the total number of legs is 118, and that comes from the total number of chicken legs and the total number of cow legs. So here's where you have to know a little bit about biology, I guess, or zoology. You have to know that chickens have 2 legs and cows have 4 legs. So if I wanted the number of chicken legs, I take K, which represents the number of chickens, and I multiply it by 2. So 2K, and I add it to the number of cow legs. Well, cows have 4 legs, and W is the number of cows, so the number of cow legs would be 4W. So 2K plus 4W is 118. There's my linear system, and now you go about solving it. Okay, so this would be a good candidate for substitution. I could easily rearrange equation 1, plug it in for K or W, plug it in, but I'm a big fan of elimination. So basically, unless I get an equation where it's like K equals something or W equals something, I'm probably going to use elimination. So what I'm going to do here, you can see these numbers don't match up, but I could easily multiply the first equation by 2, so I get 2K on the first and the second. So that's the first thing I do. So 2 times number 1 is, so every term gets multiplied by 2. 2K plus 2W equals 2 times 50 is 100. And there's my new equation 1. Now you can see I could subtract these. Now I'm just going to rewrite equation 2 underneath. You don't have to, but I just like to have it organized, see what I'm adding or subtracting. Now you can see I've got, those are going to disappear when I subtract. I've got 2 and 4, 100 and 118. Well, I don't think I talked about this when I was doing the other lesson, but when you add, it doesn't really matter what order you add, but when you subtract, the order does matter. So if I just took 3 minus 2 equation, I'm going to end up with some negative numbers, negative 2, negative 18. So I'm going to flip it around. I'm actually going to take equation 2 and subtract equation 3. So I'm sort of subtracting upside down. So 2 minus 2, gone. 4 minus 2, that's positive 2w. And 118 minus 100, that's 18. And I'm going to take that up here. Divide both of these by 2, I get w equals 9. Okay, well that's cool. What does that mean? Well, this is where the let statement is so important, because now you can go back and go, well, what was w again? Well, w is the number of cows. So we now know that Darwin Farm had 9 cows. And if that's what the question was, we could stop right there, but it was how many chickens are there? So we got to keep going. So we finish off these linear system solving, substitute the variable we just got, w equals 9, into, and we're going to put it into equation 1. So it's k plus w, and w is 9, is equal to 50. So if you subtract 9 from both sides, you get k equals 41. And that tells you the number of chickens, because k represents the number of chickens. So wrap it up with a word answer. Now, in this case, they only asked us the number of chickens. Okay, and we did have to do all of this to get the number of chickens. But we, while we got there on the path to getting that answer, we also learned that there was 9 cows. So I'm actually going to show off and just put both of the numbers in, even though I don't have to. Okay, so therefore, there are 41 chickens and 9 cows. Okay, and you could easily go back, plug the solution back for the values of k and w. You could see 41 plus 9 is 50 very quickly. 2 times 41, that'd be 82 chicken legs, and 36 cow legs. That adds up to 118. So we know we're right. And that's how you do it. So, I mean, you could look at this question and just come up with a bunch of guesses. Okay, you can't do that in this unit. Every time I ask you one of these questions, I'm going to say using a linear system technique, find the number of chickens and cows. So if you just run up and do a whole bunch of guesses and then get to the right one, well, that's great, but you didn't do it the way I asked you to. You didn't show how to use a linear system, so you have to use this approach. And you'll find that after you've done a few of them, it'd be pretty quick. So the next question, I'm going to skip this for a sec. I'm going to do this one third, because there's another one that's a lot like it, but this one is slightly more difficult. So we're going to jump down to, actually, we're going to skip number 3 too. We're going to skip down to number 4. So this is the investment problem. The one we just did was just a number problem, meaning find the 2 numbers. In this case, it was the number of chickens and the number of cows. This one's an investment problem, and basically it's always the same type of question. So let's see what this question has, and I'll tell you how it might be different, how it might change. This one is a really straightforward one. If I ask you another one like this, you just basically plug in numbers in a different place. So Tran had $10,000 to invest. She invested part of the money in a term deposit. So you don't have to worry too much about what that is, just the fact that it's a place where she put money that made some interest, okay? And that interest was 4% per year. And the rest of the investment, whatever she didn't put in, the rest of the $10,000 went into bonds, and the bonds paid 5%. Okay, and then after 1 year, she made $440 in interest. So the question is, how much money did she invest at each rate? So how much of her money did she put into the term deposit? How much did she put into the bonds? Okay, so you can see the 2 variables right there. So some of the money went into term deposits, some went into bonds. So again, you could use, you could use X and Y, or you could use T and D, but I'd really avoid using T, because T's look a lot like X's and plus signs sometimes, and it's easy to get them confused. So I'm going to use the old reliable X and Y here. So let x represent, so this will be the money that went into the term deposit. So again, don't say let x represent term deposit. That's way too vague. It's the money, the amount of money, actually. And money could be in different units as well. You could have euros and pesos and yens. This is in dollars. Not sure if it's Canadian, but let's assume it is. The money invested in term deposit. Term deposits. Now, the term deposits pay 5%. I don't really need to put that in here, but for my own benefit, I'm just going to kind of tack it on to the end there to show how much they make. And that's going to be helpful when I make my equations. I don't have to go hunting back through the words to find that. Okay, so it's right there for me. And then the y will be exactly the same thing, but it'll be for bonds. So money invested in bonds. And that actually makes, oh, sorry, I got this mixed up. Term deposits are 4%, and the bonds was 5%. Okay, so I got my variables x and y. Let's create the linear system. And the 10,000 to invest. Well, we know that part of the money went to x, went to the term deposits, and the rest went to y. So that the sum of these two amounts is 10,000. So x plus y equals 10,000. And again, this is a lot like the last question. The sum of the two variables equaling a number is normally the first equation. Okay, now the second one's more difficult. So what haven't we used here? Okay, so if you read this, we've used the 10,000. Well, we haven't used the percentages yet, and we haven't used this. So how much interest did she make? She made $440. So I'm going to make an equation that basically shows where this interest came from. Okay, so this interest came from interest from the term deposit plus the interest from the bonds. Okay, so how much interest would she have made from the term deposit? Well, it's whatever she invested, which is X dollars, times the percent, that the interest rate. So 4% of X is how much interest she made from term deposits. Now, when you're making an equation, you can't put percent signs, but 4% is actually equal to 0.04. Okay, so 0.04 times X, that's how much money interest was made from term deposits. And for the bonds, I just change it to 0.05 for the percent, and then times Y. Okay, so there's the linear equation. This one's quite simple. This one's a little more complex. Now, here's where that little trick comes in, where you have some decimals. So I would really rather not work with these decimals. So what I'm going to do is multiply. You can see both of these. I would need to multiply by 100 to move it 2 places to the right. So I'm going to multiply equation 2 times 100. And that's going to move the decimal place. So that's 4x plus 5y. And this also gets multiplied by 100. So that's adding 2 zeros to the end. Okay, and there's my new equation 3, which is really the same line, same information as equation 2. Now, so now I'm kind of working with 1 and 3, and you can see, well, this, I'm just going to multiply equation 1 by either 4 or 5, and then subtract to get one of the two variables eliminated, solve for the other. So I'm going to always choose multiply by the lower number. So that's equation 1 times 4. So 4x plus 4y equals, don't forget to multiply that by 4, that's 40,000. And that's my new equation 4, which really comes from 1. Okay, so this is much nicer to work with than that. And you can quite quickly see if I subtract these two equations, it will eliminate the x. So I'm going to subtract in the regular direction down. So 3 minus 4. So 5y minus 4y is y, 1y. 44,000 minus 40,000 is 4,000. Okay, so right away I have one of the numbers I'm looking for. Worked out very quickly there, nicely. So let's figure out what x is. So substitute y equals 4,000 into equation 1. Equation 1 is always the nice sum of the two variables. So that's x plus 4,000 is equal to 10,000. And just subtract 4,000 from both, we get x equals 6,000. Okay, now we're done all the math part. We've solved this linear system. We got x and y values that will work in both. Now we just go back and answer the question. Sometimes when you get to this point, you almost forgot what the question was. So just go back, and usually it's the last line. If the total interest was 440, how much money did she invest at each rate? And that's going to help you turn the words around to answer the question a little more directly. So therefore, how much money did she invest at each rate? Therefore, she invested so x was 6,000. This is where it's good to have a nice description here. So x was money invested in term deposits. So she invested $6,000 in term deposits. And I'll put the interest rate right beside it, 4%. And $4,000 in bonds, which gave 5% interest. Okay, and there you have your answer. You can easily go back and plug these in to see if they work. It's be a little trickier to do that in your head. So if you want to try it, just use a calculator. You'll see that it works. Okay, so just like every linear system, you'll be able to check it and make sure that you are correct. There should be never any doubt after you do one of these questions. If you check your answer and it works, well, that you know you've got it right. Okay, so let's go back to example 2. And this is a mixture problem. Tells you right in the statement. Now, mixture problems and investment problems are really similar with a little bit of a twist. And you can kind of see I've got two different percentages here, just like I had two percentages for the investment problem. And you're going to see a lot of carryover here. So what a mixture problem is you take two different concentrations of the same thing. In this case, it's acetic acid. So you have a bottle. Let me just do a little diagram over here for you. So you've got a bottle of two different concentrations of acetic acid. So 5% and 10%. So 10%, what that means is out of the whole volume of this mixture, 10% is like pure acetic acid. Okay, and out of this volume, 5% is pure acetic acid, so the 10% is twice as strong. Okay, it's going to eat away more than the 5%. Okay, now what we do is we've got these two bottles, and we're trying to make a third bottle. We're going to pour some stuff in from both, and we're going to make this new solution that is 8% acetic acid. And we actually do know the total volume here. So this is actually going to be 250 milliliters. Okay. Now, what we want to know is how much of each of these we're using to make this. Okay. So the two variables, one will be, yeah, I think I'm going to use X and Y again, even though I think on the completed paper that you'll see, I think I used F and T. So let's use X and Y here. So basically X milliliters of 5% and Y milliliters of 10% go in here to make 250 milliliters of 8%. Now here's a nice little trick. So if you use the same amounts of both of these, if x and y were the same number, you know that the strength would be exactly halfway between. So the concentration of the resulting mixture, if x and y were the same amount, would be 7.5%. Okay, that would be half and half, basically. Okay, now the fact that this is 8%, that should tell you, well, if it's going to, if it's 8%, that's more than 7.5. That means we'd have to use more of the 10% solution. So that's a nice little check. You can make sure that when you get your answer that that the y should be more than the x. Okay, so let's make our equations. Well, I guess first let's do the variables. Even though we've done a diagram here, let's do a let statements as well. So let x represent. Now again, this is really important because if you start saying acetic acid and that's it, well, that's totally useless. So what are we actually measuring here when we pour this in? What are we looking for? We're looking for the volume. Okay, it could have been anything. It could have been all sorts of other measurements like the mass or the color or something. You have to say the volume. So the volume, and if you're going to use something like volume, you got to put the units, and it's measured in milliliters because this is in milliliters. The volume in milliliters of 5% acetic acid. Okay, and then the y is just the volume in milliliters of the 10% acetic acid, and I'll just put used here. Okay, now again, the first equation will be the volume. So we took x milliliters, y milliliters, added up to 250 milliliters. So x plus y equals 250. Nice, easy first equation. Now the second one's a bit more complex. It's a lot like the interest. So if you think about it, well, I used x milliliters of the 5%. So what I'm trying to get is the volume of the pure acid that I'm using here. So I want to take 5% of the volume that I'm taking from there. So 5%, remember that's 0.05 times x. So that number there, that is actually going to be the volume of pure acid from the 5% solution. And similarly, 0.10y, that's the volume of the acetic acid from the 10% solution that we've taken. Now this one here, this is where it's different than the investment problem. Okay, so right here, we don't actually know how much pure acid's here, but we can easily calculate it. It's 8% of 250 milliliters. Okay, so you could actually calculate it right here, put it in there, but I want to show you where that comes from. So it's kind of the same style as we used here. It's the percentage times the volume, percentage times the volume. Okay, except we didn't know these two volumes, so we can't actually simplify this anymore. Okay, so now you'll see that later on we don't really have to multiply these, but you could if you wanted to. Okay, there's our linear system. Let's solve it. So again, we've got one of these, decimal equations in our linear system. Let's multiply it by something that'll get rid of all the decimals. So these two, just like the other one, multiply by 100 will get rid of the decimals, and the 100 will also get rid of that decimal. So let's do that. So equation 2 times 100, 5x plus 10y. Now here's a little trick. If I multiply the 0.08 by 100, that changes to 8, and then I can just do 8 times 250. Okay, and I can do that in my head. I know that 4 times 250 is 1,000, so 8 times 250 is 2,000. Okay, so there's my new equation 3, which is same line, same information as equation 2. And now I look back at, I got to use equation 1. So what I want to do with this, I think I would like to multiply it by 5 so that I can then subtract and get rid of the x's. So equation 1 times 5, 5x plus 5y equals, and then 5 times 250, that's 1250. And that's equation 4, which came from equation 1. And now we can just subtract. So I'm going to subtract down. I'm going to get positive values here and here. So that's going to be, that's 0. This is 5y. And this is 750. If I divide both sides by 5, I get y equals 150. So what does that tell you? It tells you that we are going to use 150 milliliters of the 10% acetic acid. Okay? Substitute that back in. Substitute y equals 150 into equation 1. So x plus 150 is 250. Well, that's pretty easy. Subtract 150 from both sides. I get x equals 100. So that means we're going to use 100 milliliters of the 5% and 150 of the 10%. And remember, that makes sense that we use more of the y, more of the 10%, because our final concentration is above the 50-50. If they were both the same, it would be 7.5%. Okay, so let's round this off. Remind ourselves of the question: how much of each should she use? Okay, therefore, she should use. So let's do the x first. So x is the milliliters of the 5% acetic acid. Okay, and that was the x, and the y is 150. Milliliters of 10% acetic acid. Okay, so you can see even the linear system looks very similar to the investment question. The only difference was they didn't actually give us this number directly, but it's easily obtained by multiplying these two numbers together. But that's the only thing that makes this one more difficult than the investment problem. But there's a lot of similarities. That's why I did these two together. Okay, last question. And this is a totally different animal, this question here. But once, like a lot of these, once you've seen one solution, it becomes not quite as earth-shattering the next time you use it. But the first time you see it, it's quite different. So this is called a current problem. So current meaning like a river current. Okay, so the situation is normally you're canoeing or kayaking or swimming down a river downstream with the current, and then you stop and come back to where you started, where you began. Okay, so let's just read this. A canoeist took 2 hours to travel 12 kilometers down a river. And the word down is actually very important. So down a river means you're going downstream, which means the current is pushing you. It's helping you. Okay. The return trip against the current, so this is upstream, it took 3 hours. And that the difference in the time makes sense. It was quicker to go downstream than upstream. The distances were the same, 12 kilometers both trips, because this is the return trip, same distance. But this time you had the current pushing against you, slowing you down. Okay, what was the average paddling rate of the canoeist? So when you say paddling rate, it's like the speed that the canoeist would paddle in still water with no current. Okay, and what was the speed of the current? Okay, so I always like to draw a quick little picture here. So this is going downstream, and then we returned, came upstream. The distance was exactly the same for both, 12 kilometers. but this downstream, so downstream, the river's actually going this way. Okay, so on this part of the trip, it's going to be quicker, right? So, and it's 2 hours. And on the return trip, fighting the current, it was 3 hours. Okay, now, when we make the equations for this, this is where the difference is. What we're going to do is we're going to make an equation for each of the 2 trips, or each of the 2 legs of the trip. Okay, and we're going to make the equation based on, you can see we've got a couple of things. We've got a, it wants to know the speed, it gives the distance, and it gives the time. So this is a great candidate to actually use this relationship between distance, time, and speed. Okay, so you may have seen this triangle in your science class, d, s, and t, or maybe dv and t for velocity. So anytime you want an equation like this, like for example, it tells you the distance is equal to the speed times time, or if you wanted the speed is the distance divided by the time, or the time is the distance divided by the speed. So we're actually going to use a version of this. I'm going to flip around the variables in the order. I'm going to do the distance equation, but I'm going to do it this way. So distance is speed times time. I'm going to say it exactly backwards. I'm going to say time times speed is equal to distance. Time times speed equals distance. Okay, so when I talk about the first trip going downstream, right away we can see it took 2 hours. So it's going to be 2. Oh, before I do that, we've got to do our variables. What was the speed of the canoeist, the paddling rate, and what was the current? So I will do, what variable should I use for this? Yeah, let's use paddling. P for paddling. Let P represent the paddling speed. And the units for that would be kilometers per hour, because the distance is kilometers, the time is in hours. So that's kilometers per hour. And let C represent the current speed. Now remember, current is not like right now speed. It's the speed of the water as it's going down the river. Okay, so back to our formula. Time times speed equals distance. So when I'm going on this first leg, the time is 2 hours. Okay, the speed. So, well, we don't know the speed. That's what we're trying to find out. But if you're going downstream, basically, if there is no current at all, your speed would just be P, right? But there is a current. Now, in this case, the current is helping you. So, for example, let's just come up with some numbers. Say the canoeist is paddling at 7 kilometers an hour, and the current speed was 3. Well, the three from the current is actually added on to your paddling speed. So even though you're only paddling 7 kilometers an hour, you're actually traveling at 10 kilometers an hour because the current is pushing you. So we need to add the 2 speeds together when we're going downstream, so that the speed will be P plus C. And I have to put that in brackets because that has to be multiplied by the 2. Both of these combined have to be multiplied by 2. And the last part is equal to the distance. Well, that's 12 kilometers. Okay. Now the next one should be very similar. So going back, how long did it take? 3 hours. Okay, I'm going to fill in my distance. I already know that's same distance. But this time the speed, because the current is pushing against you, it's actually canceling out some of your paddling speed. So it's going to be P minus C is your actual speed. Okay, so there's your 2 equations, and I know it looks a little different with the brackets. We're actually going to do something a little different here. I'm going to, instead of expanding this and then working with that new linear system, I'm going to, for the first equation, I'm just going to divide both sides by 2 because there's a 2 in front of here, and I can easily divide 12 by 2. So when I divide this equation by 2, the left side divided by 2 cancels the 2 there, and it's just p plus c. And then when I divide the 12 by 2, I get 6. And there's my new equation 3. Now, this one here, I'm not going to divide by 2. I'm going to divide by 3 because both of these can be divided by 3. I cancel out that 3 entirely. So if I divide that equation by 3, cancels the 3, so I get p minus c is equal to 12 divided by 3 is 4. Okay. Now, this is the best linear system in the world. Okay. And hopefully you can see, I could add these two equations together and it's going to cancel the c, or I could subtract these two equations, it's going to cancel the p. I don't have to do anything else with this, but I could either eliminate the p or the c at this point. I'm going to eliminate the c just because it's always easier to add than subtract. So I'm just going to say 3 plus 4, and that's going to be p plus p is 2p, c plus negative c is 0, and this is a 10. Divide both sides by 2, I get p equals 5. So that tells me the paddling speed is 5 kilometers per hour. Okay, let's go back and solve for the other. So we're going to substitute p equals 5 into, well, let's plug it into equation 3. So p, which is 5, plus c is equal to 6. So I just took it from there. I'm going to subtract 5 from both sides, and I get c equals 1. And that means the current speed is 1 kilometer per hour. And if this is going to work, the paddling speed has to be more than the current speed. Because if the current speed was faster than you can paddle, you'll never make it back on that return trip. Okay, so make sure this works. And most of the time you get a question like this, it should be in nice integers. Like, I'm not going to give you any nasty fractions. It might be 1.5 kilometers per hour, but it's never going to be anything like 5/3. Okay, so just wrap this up now. What was the speed of the current? What was the speed of the canoeist? Therefore, the canoeist paddled at a rate of 5 kilometers per hour, and the current was 1 kilometer per hour. Okay. All right, so there you go. We've done our 4 examples. I'm only going to give you questions. Well, I might give you a thinking question on the assignment, but I'm going to give you a couple, 2 or 3 of these styles to see if you can do them for yourself. There's also going to be a fair number of just regular, here's a linear system, what's its solution, what's the point of intersection. And like I said last lesson, I will be giving you one question where I ask you to solve using substitution. I'll give you another question, I'll ask you to use elimination, and then every other question I'm never going to tell you what method to use. Okay, I just want to make sure that you know how to use each method, and then from then on it's your call. Okay, so that's it. There's quite a few questions here you can try. The more you can look at and practice, the better you'll do on the assignment, because I might take some variations of these, or I might take something that I didn't assign from that page. Okay, so if you have any questions, please join me on office hours this week. The office hours will be different, just because my schedule is a little messed up. I will be posting on Monday afternoon the office hours for this week, and hopefully I'll figure out what the office hours will be for the next couple of weeks. Okay, so this is the last lesson, one more assignment, and then it's basically me marking and getting the marks back to you. So good luck on that last assignment, and please come for help if you need it. Okay, thanks guys.